All right, so while I'm thinking of it, on this test, I said it's going to be shorter than the others. It's like 22 multiple choice questions, 6 vocabulary, and 4 short answers. So it's shorter. One of the things I want you to be able to answer a question over is this idea of in the what we now know to be spiral galaxies. They just used to call them spiral nebula, and didn't know whether it was like nebula being something part of the Milky Way galaxy versus actually down here you can see the question, is it a system of stars that's far from our own, i.e. its own galaxy? So that's kind of a debate. Speaking of that debate, in the year was 1920, wink wink, when actually Shapley and Curtis went at it and tried to discuss these spiral nebula / spiral galaxies. And remember that they didn't resolve the issue then, but at least they were talking about it. But 1920, the concept of a galaxy still wasn't in place. And so the missing piece was how far away these spiral objects were. And so on your review sheet is the name Henrietta Leavitt, and she was the person who, prior to 1920, actually had discovered that the Cepheid variables would, if you look at the period of a Cepheid variable, kind of pulsating star that's left in the main sequence, you can link the period back to its luminosity, and we can use luminosity, compare it to brightness to get distance. And so that's actually what Edwin Hubble did in 1923 to know how far away these spiral objects are. And of course, he actually found out how far away the spiral nebula was. Now we call the spiral galaxy, sorry, Andromeda Nebula. We call the Andromeda Galaxy, and it's 2.2 million light years away. He used the Cepheid variable. So we generally talked about the structure of our galaxy, and of course the center of our galaxy is a supermassive black hole, but people have been wanting to kind of know where the center of our galaxy was for a while now. I have 2 things on your test that we talked about. One was William Herschel in 1780 said, well, let's just kind of look at the density of stars and we'll kind of see where the stars then we'll use the density of stars to find out where the middle of our galaxy is. And lo and behold, he came up with the middle of our galaxy is here. And on the test, it says something about what was wrong was he really can't see way deep into our galaxy from our position because of the dust obscuring our line of sight. So there's that. Different approach, and actually, so Harlow Shapley, although he was wrong on the Curtis-Shapley debate, he was right about this. So Shapley actually used globular clusters, and we now know that globular clusters kind of buzz or hover around the center of the center of our galaxy. So a supermassive black hole. So globular clusters are a way to locate the center of our galaxy. How do we map our galaxy? It's a tough one because, like Herschel found out that you can't see through the dust in our galaxy, and so 2 ways. I think one way is to actually look at our galaxy in these other wavelengths: radio, infrared, X-ray, gamma rays. And then the other is to look at other galaxies for clues. So those 2 ways to understand what our galaxy looks like. So here is a spiral galaxy what we call face on. So actually our galaxy is a barred spiral galaxy. Okay. And I have a question on there about the spiral arms in our galaxy, and I can't remember. I think it might be with regard to our place in the disk of the galaxy, what spiral arms are kind of we surrounded by. So Sagittarius arm, Perseus arm would work. We're on the Orion arm. So here we go. Yes. Orion, was it Carnian, Perseus? Okay. So this, I have a question or a hint to generally know kind of the structure of our galaxy, and we are 100,000 light years side to side. How thick we are is about 2,000 light years. I'm not sure what this 400 light years is, but 2,000 light years is more kind of the disk thickness. We have the disk, and then outside the disk we have the halo region. Of course, these little things right here are globular clusters. We are located about 26,000 light years from the center of our galaxy. So kind of know, maybe you want to be able to draw it, hint, hint. The supermassive black hole in our galaxy is a region called Sagittarius A star. So it's A star with a little asterisk here. Yeah. One of the things about our galaxy and actually other galaxies is this is a rotational curve. So this is like how fast it takes for stars to orbit the center of our galaxy as they get farther and farther from the galactic nucleus. So the red line, remember, is what it does, and the blue line is what we thought it should do, what Kepler's law says. And the fact that it stays, we have these high rotational velocities very far from the galactic center, means that actually, like this caption says, we must have a fair bit of mass that is outside, that we can't, outside the galactic nucleus, outside the supermassive black hole that we can't see, and that's dark matter in the halo region. So we have, we have this dark matter in the halo region, and most galaxies have it. We'll talk more about dark matter in Unit 5. So this is kind of what our galaxy looks like. So this is the disk of our galaxy, this is the nuclear bulge, this is the halo region. In the halo region we have dark matter. All right. There's a question on there about our sun and how long does it take to complete one cycle. Our sun's a star, right? Orbiting the supermassive black hole in our galaxy. How long does it take the sun to complete one orbit? And the answer is, dun dun dun, 23 million years. All right. All right. There's also a question about how do we know that there's supermassive, that Sagittarius A star is a supermassive black hole. And these, I think this is pretty cool, where these are actually stars that have been tracked over a 9-year period of time orbiting Sagittarius A star. And remember that you can look at the motion of an object in orbit like these stars and then understand the mass of the object that they're orbiting by looking at their orbital motion. So anyway, that's how we know that we basically have a very dense object. We have a very massive object, 2.5 times 10⁶ solar masses, in a very small area. So it's very squished down. So that is a very dense object, supermassive black hole. All right, on to the next part. Edwin Hubble. On your review sheet, you have, and on your test, you're going to want to be able to say what the 4 main types of galaxies are. And this is what, if I think of the 4 main types of galaxies, this is what I'm going after. I'm going after spirals, barred spirals, ellipticals, and irregulars. And then this is Hubble's tuning fork, and here we have the ellipticals, and here's the spirals, and here's the barred spirals. So a couple of test questions. One is kind of what I call subtle differences. So remember we said the ellipticals, if it's real circular, it's E0. If it's elongated, it's E7. So eccentricity increases with increasing number. And then subtle differences with our spirals, whether it's spirals or barred spirals. Remember we said that, I'll go clear out here to the C's. With these loosely wound arms, remember that they have the thinnest nuclear bulge. Okay, loosely wound arms, thin nuclear bulge. I can go over here to the A's, or SA or SBA, and the arms are tightly wound and has a thick bulge. So kind of know those. And then in general, kind of know the anatomy of a galaxy. It generally has a disk. It has a bulge, supermassive black hole most likely, with spiral arms. On to the next part. Galaxies are organized in families called clusters, and our cluster is called the local group. Like Cheers, right? Okay. What else do we have? And then the clusters are further organized into superclusters. Go figure, right? We are part of the local supercluster, I think. But these superclusters, or the galaxies clusters, are organized around these void areas. So, excuse me, the void area would be like a sponge, like that's a void, that's a void, that's a void. And so there's emptiness there. No galaxies at all, no clusters of galaxies, no superclusters. All right, on to the next part. Of this part, what I picked out was galactic cannibalism. Remember, the difference between a galactic merger versus a galactic cannibalism is, in a cannibalism, you basically have one really big galaxy that is gobbling up a smaller galaxy. I think that is so. I like that term. All right. So on this slide, I want you to know cosmology. Cosmology is the overall study of how the universe is structured and how the universe has evolved over time. I don't think I necessarily specifically need to know anything about anything else on that slide, other than the concept of a standard bulb. Speaking of standard bulb, the one standard bulb I picked out, I think maybe just one, was this white dwarf supernova type 1a. Now remember, you're going to need to know what happens with this white dwarf supernova type 1a. This is where you have a retired star that has a swollen companion, is getting dumped on by its swollen companion. It gets dumped on beyond that Chandrasekhar limit, and it blows up. What makes it a standard candle is that it blows up with the same brightness all the time, because it's got that critical 1.4 solar masses before it blows up. So a standard candle means that we know its luminosity, and then a few, like the previous slide said, and we talked about in class, if you know its luminosity, you can compare it to what it looks like, its brightness, and then you can do a little bit of math and get to its distance. So there you go. This one, so I wasn't necessarily the Cepheid variable for distance, although we do know that Hubble used a Cepheid variable in the Andromeda Galaxy to understand the Andromeda Galaxy is 2.2 or 2.5 here, 2.2, 2.5 million light years away. My point here is this idea of this down here. Okay, we're at this point in the lecture, we were kind of segueing way into talking about the expanding universe, and the galaxies are all, in general, some are merging, but in general, all the galaxies are moving away from us. And so things are moving away from us gives us this red shift. And that's shown right here. So the universe is expanding. That is so cool. Let's see. We call this expansion in general Hubble flow. Maybe that was what I was trying to say here. So Hubble's law then actually says that the farther away the galaxy, this is the farther away the galaxy, the faster its recessional velocity. So that would be Hubble's law in general. And then kind of finished up in talking about different ways of telling distances. So these are ordered in order of closest to farthest away. So we can use radar for close things, parallax for a little farther things, sequence fitting, then Cepheid variables, and then distant candles, distant standards such as white dwarf 1a supernova, and Hubble's law. So kind of know the order of getting farther and farther away with those techniques. All right. So then this actually revisits the idea of according to Kepler's laws and Newton's laws, we expect kind of the stars to slow down as they get farther away from our galactic nucleus, but instead actually they are showing here to kind of speed up. So this observed difference in the orbital nature of our stars outside on the edges of our galaxy means that there's more mass, and as I said, it's located, that mass is dark matter located in our halo. Can't remember what I was doing here. Well, another thing is this idea of what dark matter can do, which all matter can do, is actually cause a sort of dent in the fabric of space-time that we talked about before, and this dent then actually can create a place where starlight can be bent, and we call this gravitational lensing. And then I included this as actually gravitational lensing in action, where you can kind of see the blue sort of things like that actually is a distant star that light is being bent and lensed. Is that the last one? Oh, one more. Okay. One of the things on your test in general is this idea, and we talked about this clear back in Unit 1, that as we're looking at these galaxies that might be 2.2 or 2.5 million light years away, like the Andromeda Galaxy, that means it took, in the case of Andromeda, 2.2 million years to get to us. And so we are looking at that galaxy as it was 2.2 million years ago. Well, if we go ahead and think about this, then if we're looking at these galaxies that are about 12 or 10 to 12 billion light years away, then we are looking at them as they were just 2 million years or so after the Big Bang. So that's kind of how that works. These are very young galaxies. There is a question about the evolution of galaxies. Now, remember, there are four main types of galaxies, but if you kind of put spirals and barred spirals together, you kind of just have ellipticals and spirals. And as it turns out, kind of the evolution of them depends a little bit on the condition of their protogalactic cloud. So have a couple of different scenarios down here, and you're going to want to know what gives us elliptical galaxies and what gives us spiral galaxies. Elliptical galaxies, spiral galaxies. What this first one is kind of showing you is that with rotation, I'll go down here to spiral. With rotation, you get spiral galaxies. Kind of makes sense, right? And the other thing with spiral galaxies is you need to have a protogalactic cloud that isn't too awfully dense. So with rotation, you get spiral galaxies, and with kind of a low density cloud, you get spiral galaxies. So then the opposite is true with regard to elliptical galaxies. If it's not spinning, elliptical galaxy. If it's nice and dense, elliptical galaxy. And then this last one, and you actually 2 slides ago saw this too, as we look back at those very young galaxies, the galaxies that were formed shortly after the Big Bang, they tend to look all kind of smeary and distorted. And so we kind of see that change as they evolve and become ordered. That's it.